All right, so in this video, we're going to be talking about something called the eigenvalue-eigenvector problem. Eigenvalues and eigenvectors end up becoming really important throughout a lot of applied mathematics, physics, computer science, electrical engineering. They just have a really huge value, and they're kind of an interesting mathematical entity as well. So what we're going to talk about here inside of this lecture is we're going to talk about what is an eigenvector and eigenvalue. We'll talk about graphing eigenvectors and also confirming that we have eigenvectors and eigenvalues. Then we'll talk about the process for finding eigenvalues, and then we'll talk about the process for finding eigenvectors. All right, and then we'll give some examples of how to do this and show you some ways to do that. And then we're going to talk about some of the key vocabulary that you'll need in order to talk about eigenvectors and eigenvalues. So let's first talk about this question: what is an eigenvalue or an eigenvector? Okay. So a vector or non-zero vector V, okay, is called an eigenvector for a square matrix A if there exists a constant, either complex or real, lambda, which we call an eigenvalue, not an eigenvector, such that AV equals lambda V. Okay, so what exactly does this mean? Let's look at this algebraically, and we'll give a couple of examples of this. So let's suppose that I have a matrix, okay? So I've got a matrix, and the matrix is this matrix here. It's going to be A equals -2, 5, 6, -1. And I have a vector V, and V equals -1, 1. I'm going to take it, and I'm going to multiply A times V. So AV, okay, you can go through this. You can pause this if you'd like to, or you can just take my word for it. Got -2, 5, 6, -1. Multiply it by -1, 1. And what I get is I get -7, 7. Okay? I get -7, 7. Now what you want to notice is that -7, 7 is a scalar multiple of V. Okay? It's a scalar multiple of our vector V. And so what this is this is AV, right? A times -1, 1 equals 7 times V. Okay? So -1, 1 is an eigenvector, and lambda equals 7 is its eigenvalue. Now what we want to get is that we don't have to necessarily have just one eigenvector or just one eigenvalue. We can have multiples. And in fact, much of the time we do actually have multiples. So for example, if I take -2, 5, 6, -1, okay, and I'll call this lambda 1 by the way, times, and let's take our V now to be 5, 6, and this ends up equaling, if you go and you do the multiplication, what you end up with is you end up with 20, 24. And what you'll notice is that then AV, my matrix times V, is equal to 4 times, in this case, 5, 6, which is my vector V. So lambda 2, my eigenvalue, is equal to 4, and we'll call this V2. My other eigenvector is 5, 6. So that gives you kind of an idea of what it is to be an eigenvector and what it means to be an eigenvalue. Okay? And one of the ways that we go through to confirm that we have an eigenvector or an eigenvalue, and we'll do this kind of like very rigorously, is we just go in and we multiply the vector times the matrix and see if we get a scalar multiple. Okay? A scalar multiple of our vector V, and if we do, then what we have is an eigenvector, and whatever the scalar is ends up being the eigenvalue. So what we just saw was we saw a vector V that when we went in and we multiplied it by A, we either stretched or shrunk the vector V, right? Basically we scaled it, okay? And so if we imagine that A is a linear transformation, we can imagine that T of V, my linear transformation, is going to equal lambda V. So basically what the transformation does to this vector V is that it actually just goes in and it just stretches or shrinks the vector, and it could possibly, rotate the vector, right? What it does not do is it doesn't change the direction of that vector. So for example, if I imagine that A that we saw before, right? So we had, in this case, we had A equals -2, 5, 6, -1. And we imagine that as the linear transformation. So this, well, let's let this be t, the associated linear transformation t of v, okay? And we start out with this vector -1, 1. So remember, our first vector was -1, 1. This vector right here, okay? So there's that vector. And then under the transformation, what happens to that vector is that it gets scaled. It got multiplied by 7, right? So we had the vector v equals -1, 1, and we had lambda equals 7, and so our transformation is going to take that now to -7, or, well, it's going to stretch it by 7. 1, 2, 3, 4, 5, 6, and 7. And so that's our new vector, okay? Here's AV. This is AV, the transformation of V, okay? So its direction remains exactly the same. It still has the same exact direction. The difference, though, is that it's now been scaled, okay? And notice, what is it? It's 7 times the vector V. Conversely, what we can do is we can think about our other vector, okay? We'll have our V2, and that equals 5, 6. So we had 5, 6. So that's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. And that vector under the transformation, so here was V2, here's V1, here's V2, and what you're going to get is you're going to get, right, it's going to get scaled. So 5, up 6, okay? And so you can imagine it's actually going to go out quite a lot, right? We're going to continue to go in that direction. And this new vector now is going to end up being 4v. That's the stretching. And it also is then AV, right? It's under the transformation, we're going to get AV, which equals 4v, and so it's stretched the vector. Now, if you kind of think about this from the standpoint of a change of basis matrix, or a matrix of the transformation, what we've got here is we've got a set of basis vectors. We've got V1 and we've got V2. And so what we know is under this transformation that V1 gets stretched by 7 and that V2 gets stretched by 4. So if what we do is we go out and we write all of, if we write our basis, right, in terms of these two vectors, -1, 1 and 5, 6. So we construct the space R2 in terms of this basis, then we know exactly what happens to every vector under that basis, okay? What we're going to do is we're going to stretch each vector written in the basis. The one that is -1, 1 under the basis, we're going to multiply it by 7. And the other one that corresponds to 5, 6, we're going to multiply it by 4. Okay? And so what you can kind of imagine is you kind of imagine a really very clean way to represent every single vector under this transformation. Right? And that's kind of the thing that we do with eigenvalues and eigenvectors. We imagine that they are transformations, right, that give us very convenient bases that we can, or excuse me, they are very convenient basis vectors that tell us what a transformation does, or what a matrix does, okay, to all of the vectors inside of a space. All right, so like in this case, we said stretch one set by 7, stretch the other set by 4, okay, because lambda 2 equals 4. So they give us a lot of really good information, okay. So let's think a little bit more on the geometry here, and let's suppose that we have this matrix A equals -1, 0, 1, and then A reflects every vector over the y-axis. So we're going to use a geometric argument to determine the eigenvalues and eigenvectors. So we've got this transformation, and what this transformation does is it's going to reflect everything over the y-axis. Okay? So if you imagine what that means, say, for example, we're going to get... if we have 2, -1, that's going to go out to 2, 1. Right? That's going to be that reflection over the y-axis. Okay? Excuse me. -2, 1. Sorry. It's going to be -2, 1. Sorry. That's what I meant. Or, like, for example, if we have 3, 2. 3, 2 is going to go to negative 3, 2. Okay? So we've got, say, for example, 2, 1 goes to negative 2, 1. There's my reflection over the y-axis. Or we've got, like I said, 3, 2. Vector. And, well, 3, 2, that vector, and then 3, 2 being its reflection. Okay? So basically that's what's happening there. So we can imagine that's what's going to occur when we draw these vectors. So now what I want to do is I want to ask myself, what vectors when I reflect them over the y-axis will be in the same direction. Now you'll notice that those other vectors, they actually switched directions. They changed directions. They were no longer in the same direction. So I need to figure out when I reflect something over the y-axis, which ones are going to remain in the same direction. So the first one I'm going to think about is this standard basis vector. Okay? The standard basis vector 0, 1, or excuse me, 1, 0. So 1, 0, when I reflect over the y-axis, is going to go to negative 1, 0. So 1, 0 will go to negative 1, 0, right? It remains in the same axis. We're just reflecting it, right? Notice it's just, that equals negative 1 times 1, 0. So that actually looks like it would be an eigenvalue for me, an eigenvector, and I've got an associated eigenvalue of negative 1. The other one is a little bit more tricky. So it could be, let's see if 0, 1 actually does it too. So 0, 1, notice is on the y-axis. So 0, 1 is actually going to go to 0, 1. It's not going to reflect at all. So it is equal to 1 times 0, 1. And so that ends up being my other eigenvalue. Okay? Now a couple things to note here. One thing is to note is that I can scalar multiply any of these, and I'm going to use a different color to kind of demonstrate that. If I wanted to, I could have used, I could have used 4, 0, and it would have gone to negative 4, 0. Okay? Or I could have used, say, for example, negative 3, or 0, negative 3, and it would have gone to 0, negative 3. Okay? It turns out that every scalar multiple of an eigenvector remains an eigenvector with the same associated eigenvalue. And the reason why this is the case is because we want to imagine that vectors are all pointing in the same direction. If they're pointing in the same direction, from a linear algebra perspective, they're pretty much the same, right? Scalar multiples are linearly dependent, and so pretty much they're going to kind of act the same. We can pretty much treat them the same, all right? So it turns out that if you utilized, say for example, you said, oh, okay, well instead I'm going to use 3, 0, okay, and it'll go to negative 3, 0. That's still true. You use 3, 0 as your eigenvector. You'd say negative 1 is still your eigenvalue, okay? And you would still have a valid set of vectors, okay? Or you could say, okay, well, I'm going to use 0, negative 2. It'll still go to 0, negative 2, and we still have the same eigenvalue of 1 times 0, 2. You can do the same thing up here, too, that we're doing. If we chose a scalar multiple of negative 1, 1, okay, so say, for example, I chose a scalar multiple of negative 1, 1. Let's say negative 2, 2, all right? So we've got negative 2, 5, 6, negative 1, and we're going to multiply it by negative 2, 2, okay? Well, if I rewrite this, right, I know that this is going to end up being negative 2, 5, 6, negative 1 times 2, negative 1, 1. And that equals then 2, and well, that's just a, 2 times AV. 2AV, which we already know is going to end up equaling 7 times V, because that's what our transformation does. So this ends up being 2 times 7 times negative 1, 1. And so it ends up being 14, or negative 14, comma 14. All right? Which is just 7 times negative 2, 2. So you can see that the scalar multiple is actually going to remain an eigenvector. It's just, and in fact, it is the same eigenvector. You can divide it through. It's in the same direction. We can utilize it as a basis vector, and it's going to give us the same basis. Well, it's not going to give us exactly the same basis, but it's going to give us the space written pretty much the same way. Okay, and so consequently, there's a lot of different choices that we can make. All right, working geometrically to find our eigenvectors and eigenvalues. You could choose any scalar multiple in this case. Now, let's take a look and see if this is actually true. So, allow me to go back to black. I've got -1, 0, 0, 1. I'm going to multiply that now, and we said that 1, 0, we expect that to go to -1, 0. Well, I get -1 when I multiply it, and then 0, which is -1 times 1, 0. There's my eigenvalue and eigenvector. So lambda 1 equals -1, and v1 is going to equal 1, 0. And then I'll take the other vector, -1, 0, -1, 0, 0, 1. We'll multiply it by 0, 1, my other eigenvalue, okay? And that equals equals 0, comma 1, which is 1 times 0, 1. So that means lambda 2, my other eigenvector, or eigenvalue is 1, and my other eigenvector is the other standard basis vector. Okay? So essentially what we can do, or what we want to do, is it takes a little thought, it takes a little focus and concentration, but what we can do is we can actually, if we're told what the transformation does, or what the matrix does to the space, there's a very real possibility that we can actually get out or find our eigenvalues and eigenvectors by considering which vectors will remain in the same direction. So we want to ask ourselves, which vectors will remain in the same direction under A or T, if it was like associated with A. Okay? And so that kind of helps us to kind of think about what happens to a space geometrically a little bit more. Now what we're going to do is we're going to talk about the general process for finding eigenvectors and eigenvalues. It's going to require a lot of linear algebra. Makes sense, right? Okay. And so consequently, what we're going to do is we're going to begin with this very simple concept. We're going to begin with the idea that AV equals lambda V. Okay. And we're going to have that V does not equal the zero vector. Clearly, the zero vector remains invariant under every transformation. V being the zero vector is trivial. Okay. So if we actually do end up with 0 as one of our eigenvectors, we got a problem. We got an issue. Okay? So consequently, and we'll talk about that issue in just a little bit. So consequently, we're going to assume that V does not equal 0. So we're going to take AV minus lambda V is going to then equal 0. So we're going to subtract lambda V from each side. And now what I'm going to do is I'm going to rewrite. We're going to let lambda is going to equal lambda, or excuse me, what we're going to do is we're going to make this A minus what we call lambda I, and we're going to factor out V. Now, lambda I is just, I is our identity matrix, okay? So it's 1, and it's got, 1's all the way down, and then 0's everywhere else. And we're going to multiply by lambda, so what we get here is we get a matrix with lambdas along the diagonal. Okay, we got this matrix with lambdas down the diagonal and zeros everywhere else. And if you think about it, okay, that actually is, if we multiply lambda I times V, we get literally lambda V. Okay, get lambda V because all we're going to do is we're going to multiply, right, lambda times the first part, zeros everywhere else, lambda times the second part, zeros everywhere else. And you can actually kind of go test that out and see what happens. So that's then going to equal 0 still. Okay? Now, A minus lambda I is an n by n matrix. All right? I should state that we are only going to be finding eigenvectors and eigenvalues for square matrices. Okay? So I'll add that in here. A is square. Okay? N by n. Because there are no eigenvectors and eigenvalues for non-square ones. There we go. So A is an n by n matrix, or A minus lambda I is now an n by n matrix because we're just n by n, n by n. I should make this in. So what we have here is we have a matrix times a vector equals 0. We have a matrix times a vector equals 0. And so we have an issue. V, that vector V does not equal 0. Okay? So we have a non-zero vector times A minus lambda in. Okay? And it will equal 0. And what that means is that means the column vectors of A minus lambda I are linearly dependent. So the column vectors of A minus lambda I are linearly dependent. All right? So what that means, right? And so if you think about it, that means that the solution to AX equals 0 has a non-trivial solution, right? Non-trivial solution. So the result of that is that means that the determinant of A minus lambda in is equal to 0, right? So if you remember, I've got a square matrix, okay? And I have that the column vectors of A minus lambda in are linearly dependent. So the determinant of A minus lambda in has to equal 0 by the IMT, by the invertible matrix theorem. Okay? The solution to the determinant of A minus lambda in equals 0 are the eigenvalues of A. So we're going to see that, and that's the first step here. That actually helps us to determine our eigenvalues. We're going to go in, we're going to say, okay, well, the determinant of A minus lambda I equals 0. We'll solve for lambda, right? Okay, so basically we're going to solve for lambda, and when we do, after we solve for lambda, that's going to be our eigenvalues. Those are going to be our eigenvalues, and this is why. Okay? Takes a lot of linear algebra, but it's pretty straightforward. When you see it done, you're going to be like, okay, I got to get it. Okay? Now, what we're going to get then is we're going to say, okay, well, let's let lambda be an eigenvalue for A. Again, we've got AV equals lambda V. And so by the way, this is the process to solve for the eigenvectors. I got AV equals lambda V. A minus lambda I, V is going to equal 0. Okay? We want to know V. The set of V's, okay, the set of V's such that A minus lambda I V equals 0 is the null space of A minus lambda I. Okay? So it's the null space of A minus lambda I. Think about it for a moment. You're like, okay, right? Like, I'm trying to solve this system. This is the homogeneous system. Okay? The solution to the homogeneous system is the null space of the matrix. That's it. Okay? That's the process that we're going to use in order to solve for our eigenvectors and eigenvalues. We start out, we're like, okay, cool. I know this fact, AV minus lambda V equals 0. We get this matrix here, A minus lambda IV, which we're going to talk quite a lot about. Okay? And in order to find the eigenvalues, we're going to take the determinant. Okay? And then once we actually find the determinant, or the solution to this thing right here, okay, determinant of A minus lambda I equals 0, we're going to get the eigenvectors, okay? We'll plug in an eigenvector. Once again, subtract lambda, and it'll turn out lambda from the diagonal of A. And then we're going to solve for the null space of that we're going to solve for the null space. We're going to solve for the null space of a minus lambda I. Okay, that's it, right? Cool. By the way, this thing right here is called the characteristic equation, and you're going to see when we actually solve it, it's going to actually be an equation. It doesn't look like one right now, but that's called the characteristic equation. We're going to actually go through and solve for it. So we're going to actually find the characteristic equation for a particular a, and it's going to end up being a polynomial. So we're going to get the characteristic equation is when we solve it for 0, and the determinant of a minus lambda I is called the characteristic polynomial. And you'll see why that's the case as well. All right? Cool. So there it is. Let's go do some. So let's do an example. Let's find the eigenvalues and eigenvectors for a equals 5, -4, 8, -7. So the first thing I want to do is define lambdas, my lambdas, okay? Might be 1, might be 2 in this case. I want to find my lambdas. And so a minus lambda I, what that looks like is that's going to look like 5 minus lambda, -4, 8, -7 minus lambda, right? You can go in and check it, like take the 2 by 2. If you took 5, 8, -4, -7, minus, in this case, lambda, 0, 0, lambda, you're going to get exactly what we got here, okay? And that's all I did. I'm going to erase this, but that's what happens. So we did that. And now I need to find the determinant. So the determinant of a minus lambda I is going to equal 5 minus lambda times -7 minus lambda minus -32. This is then going to be, I'm going to factor everything out in this case. I've got -35 plus 7 lambda minus 5 lambda. That's a 7. I don't know why it looked like that. 7 lambda minus 5 lambda. Plus lambda squared plus 32. So this ends up being, so lambda squared. This ends up being -3 plus 2 lambda plus lambda squared. And that ends up equaling the determinant of a minus lambda I. All right, so if we look at this, we now have what this thing here. This is going to be my characteristic polynomial. What I'm going to do is I'm actually going to go in and I'm going to factor it. And so what we have is we're going to have something minus lambda, okay? And so I guess this is going to be that we've got, this is going to be -3 minus lambda, and this is going to be 1 minus lambda, okay? And so consequently, this is also the characteristic polynomial. We can actually choose either one of them. Our characteristic equation then, okay, so our characteristic equation is then going to be 1 minus lambda times -3 minus lambda equals 0. And so by going in and solving this, 1 minus lambda equals 0, or -3 minus lambda equals 0, we end up getting lambda equals 1, or lambda equals -3. So we'll have lambda 1 equals 1 and lambda 2 equals -3. And these are the eigenvalues for A. So we first start out by solving for the eigenvalues for A by solving or the characteristic equation. Basically, the determinant of A minus lambda I equals 0. And that's how we go about doing that. Now that I have my eigenvalues, now I need to find my eigenvectors. And if you remember, the solution for my eigenvectors, or how I find my eigenvectors, is by finding the null space of A minus lambda I. Okay? So this is A minus lambda I right here. Okay? But we're going to do that for individual values of lambda. So lambda 1 equals 1, and then lambda 1 equals lambda 2 equals -3. So we'll take first, we'll find the eigenvectors for lambda 1. Lambda 1 equals 1, and our matrix is going to be, it's got 5. We're going to have 5 minus 1. Okay. 5 minus 1, negative 4, 8, and negative 7 minus 1. Let me just ensure that I actually have that all written out correctly. 5 minus 1, negative 4, 8, negative 7 minus 1. Okay? So that's for lambda equals 1. And so this is going to then equal 4, negative 4, 8, negative 8. Okay? I need to find the null space of, and how we write this is going to be a minus I. Okay? Because it's a 1. We no longer have the a minus lambda, it's just a minus I. Find the null space of a minus I. So I take the RREF of 4, negative 4, 8, negative 8. And what I get is this is going to equal 1, negative 1, 0, 0. Rewriting, I get that x1 minus x2 equals 0. Okay, and then x2 ends up being free. All right, so my vector now is x1 equals x2 and just simply x2. And so if I can write that, the basis here for that null space, okay, is going to be t times, or excuse me, the actual space is going to be t belonging to the reals, and 1, 1. All right? We're just going to write that vector. We'll call it v1. My first eigenvector is going to equal just 1, 1. We don't actually have to write the t associated with it. We just write it as a single vector. And then we're going to say lambda equals 1. So that is an eigenvector and eigenvalue and its associated eigenvector. Now, let's go in and use lambda 2 equals. We're going to do lambda 2 equals negative 3. We'll plug in. We're going to get 5 minus a negative 3, negative 4, 8, and negative 7 minus a negative 3. So this is then going to give me now 8, negative 4, 8, negative 4. When I take the REF, I'm going to find the null space. Find the null space of, in this case, the null space of a plus 3i, because lambda is now negative 3. And what I get now is I'm going to get 2, or excuse me, I'm going to get 1, negative 1 half, 0, 0. Okay? 1, negative 1 half, 0, 0. And that's my RREF. The RREF of a plus 3i ends up equaling 1, negative 1 half, 0, 0. Right? We're going to go find the null space. So we get x1 equals 1 half x2, right? Because we're just going to subtract over. x2 is going to be free. So what we get here is we're going to get 1 half 1. How you're often going to see it written instead is you're instead going to see it written as 2, 1. So the vector 2, 1 is going to be our other eigenvalue. Oh, excuse me, eigenvector. And oftentimes that's just because, or excuse me, not 2, 1. It's going to be 1, 2. 1, 2. And that is because what we want to do is we actually want to have whole number values for our eigenvectors. For some reason, if you can do it, that's how you're going to swing it. Okay? So if you're looking it up in the back of the book, it's going to look like that. Okay? So our eigenvalue, lambda 2 equals negative 3, and its associated eigenvector, v2, is going to equal 1, 2. And that actually gives me my eigenvectors and eigenvalues. Reviewing a little bit, we start out, we're going to find the determinant of a minus lambda I with an unknown lambda. So basically we're going to subtract lambda from the diagonal. Subtract lambda from the diagonal and then take the determinant of that matrix. Once we've taken the determinant of that matrix, what we're going to do then is we're going to find this characteristic equation and we're going to solve the characteristic equation for our eigenvectors, however many there actually might be. Then I'm going to go find my eigenvectors. How am I going to do that? I'm going to plug in my eigenvalues into a minus lambda I. So basically subtract the eigenvalue from the diagonal, okay, and then find the null space of that matrix. Or yeah, find the null space of that matrix, and the null space of that matrix is your set of eigenvectors. Sometimes you might have more than one, and we'll see an example where that actually is what happens. And then we do that for every single one of our eigenvalues. Once we do, we have a set of our eigenvectors and their associated eigenvalues. Now let's find the eigenvectors and the eigenvalues for A equals 1, 0, 0, 0, 0, 1, 0, negative 1, 0. And we're going to see something slightly different here, but that's something that we can kind of work with is still the case, or that we can still work with. So we're first going to have find A minus lambda I, okay? And I'm just going to write that out just to remind you of what it is. It's going to be 1 minus lambda, 0, 0, 0, 0 minus lambda, 1, 0, negative 1, 0 minus lambda. And so that actually is A minus lambda I. We're going to take the determinant of A minus lambda I. And so that's going to end up equaling 1 minus lambda times, and we're going to, multiply here by 0 minus lambda times 0 minus lambda, and then plus 1. And then this is going to be minus 0, and you'll notice that both of these are going to end up being zeros. So this is going to 0 times, and just as a reminder, it'll be 0 times 0 minus lambda, minus, and then this is 0 times 1, so that's just still 0. And then plus, we're going to get 0 times, and this is going to be 0 times negative 1 minus 0 times 0 minus lambda, which is still just 0. So everything's going to zero out except for this piece right here, okay? So what we get is we get 1 minus lambda, times negative lambda times negative lambda plus 1. And so that means that we're going to get lambda squared minus lambda cubed plus 1 equals 0. Okay? So what I need to do is I actually need to kind of figure out what exactly this is. Actually, it's going to be times this whole thing here. Okay? So that's going to be 1 minus lambda times, and then this is going to be lambda squared plus 1. And so what we get here is, this is now our characteristic polynomial. So it's characteristic polynomial. We're going to set that equal to 0 to make our characteristic equation. And so that's going to be 1 minus lambda times lambda squared plus 1 equals 0. Solving that, we're going to end up getting lambda equals 1, and the solution to lambda squared plus 1 equals 0 is lambda equals plus or minus the square root of negative 1, or plus or minus I. So what we have now is we have complex eigenvalues. So we've got complex eigenvalues, and that's totally allowed. There's nothing wrong with that, okay? It kind of makes sense. You're going to get polynomials that are going to have complex roots, and so consequently you should account for the fact that you've got complex eigenvectors and eigenvalues. So what we're going to do now, though, is we're just going to do the same process. We'll start out with lambda equals 1. Okay, so we'll take lambda equals 1, and we're going to plug that in, and we're going to get a minus I. And so a minus I is going to end up being 0, 0, 0, 0, negative 1, 1, 0, negative 1, 0, negative 1, negative 1. All right, and that's just taking, here's a minus lambda I. We'll plug in our the 1 in here, subtract 1 from the diagonal. And now what we need to do is find the null space of a minus I. So we'll take the RREF of a minus I. And what we end up getting here is we're going to end up getting, this is going to end up equaling 0, 0, 1. Actually, we're going to switch this around. We're going to make this 0, 1, 0, 0, 0, 1, 0, 0, 0. So consequently, what we get is we get x1 is free, x2 equals 0, and x3 equals 0. So what we can rewrite that as, we can just write that as 1, 0, 0. So that standard basis vector 1, 0, 0, okay, because we've got the free variable. So consequently, our lambda 1 equals 1 has the associated eigenvector v1 equal to 1, 0, 0. Now what we're going to do is we're going to go in, we're going to plug in I now, plug in I, and I for lambda equals I. And it makes sense that whenever we have complex eigenvalues, we're going to also have their conjugates. It's got to be the case. So now we need to plug it into this, okay? So that's going to be then 1 minus I, 0, 0, 0, negative I, 1, 0, negative 1, negative I. We'll find the null space of A minus I. A minus little I, big I. Okay? And so to do that, we'll find the RREF of this matrix of A minus I. I plug that into my computer, and I get 1, 0, 0, 0, 1, I, 0, 0, 0. So we get that x3 is going to end up being free. So we've got x1 equals 0, x2 plus I x3 equals 0, and then x3 is going to be my free variable t. We make that x2 equals negative I x3. And so when I rewrite my vector is going to simply be x, or actually in this case v. v1 is going to equal 0, negative I, 1. So lambda 2 equals I, and we get v1 equals 0, negative I, 1. Now we've got to figure out for lambda, call it lambda 3 equals negative I, all right? We'll take A plus I, okay, and that's going to end up equaling 1 plus I, 0, 0, 0, I, 1, 0, negative 1, I. Okay, and again, all I've done there is I've added negative I along the diagonal to find my null space. I'm going to find my null space of A plus I. So I'm going to have to go find the RREF of A plus I. Plug that into my computer, and what do I get? I plug in my stuff, and what do I get? I get 1, 0, 0, 0, 1, negative I, 0, 0, 0. Okay? And now all I've got to do is go out and find my null space, right? So that is the row reduction. I get x1 equals 0, x2 minus I, x3 equals 0, and then x3 ends up equaling a free variable t. So my v3, my associated eigenvector is 0, positive I, right? Because we're going to get x2 equals I, x3, positive I, 1. And the associated eigenvalue with that, L3 is equal to negative I. So if I write it all down, what do I get? I've got L1 equals 1. It has the associated eigenvector v1 equal to 1, 0, 0. L2 equals I. It has an associated eigenvector v2 equals 0, negative I, 1. And then I have L3, my third eigenvector, is going to equal negative I. L3 is the eigenvalue, excuse me. Negative I, and then v3, the eigenvector, is going to equal 0, I, 1. And that completes the finding of our eigenvectors and eigenvalues for this matrix A. It happens to have complex ones. What are you going to do, right? Now, let's go in and actually see what happens if I multiply A. Remember my A was equal to 1, 0, 0, 0, 0, 1, 0, negative 1, 1. All right, 0, negative 1, 0, right? there was my original matrix. What happens if I multiply it now by 0, negative I, 1? What if I wanted to verify, right? So I want to verify this is an eigenvector. Well, let's see. I get 0 plus 0 plus 0, so I get 0. Top part, that works. Should still be 0. Then I have 0 plus 0 plus 1, that's 1. And then I have 0 plus I plus 0, and so that ends up giving me I. Okay? So now, take a look here. I want to know, well, what do I have to multiply, or rather, what do I have to divide by, okay, in order to give me, let's say, actually, to give me 1, right? So if I divide by I, okay, I'm going to take I, and if I multiply that by 0, negative I, 1, let's see. Well, that's going to equal 0. This is actually going to equal negative I squared, which is 1. And then this is going to equal I. And so you can see eigenvalue, eigenvector. And we verified. And so that's the last little piece that we've got here for this particular lecture. Okay? So we started out talking about what is an eigenvector and what is an eigenvalue, right? The eigenvector is AV equals lambda V, right? That is the definition of what it means to be an eigenvector, is the vector V that allows AV to equal lambda V. Lambda is called our eigenvalue, okay? We talked about how it is that we go through to find, then we talked about what does it mean to graph them. And so what we see here is that under our transformation A, what ends up happening with our eigenvectors is that they stay in the same direction, but they're either stretched or they're shrunk, they're scaled. Okay, and that's basically what happens to an eigenvector or eigenvalue when we actually go in and we transform them. All right, and that ends up becoming really handy for a lot of different reasons. Once we talked a little bit about how we might actually utilize those facts in order to find eigenvalues and eigenvectors, we developed our method for finding the eigenvalues and eigenvectors. Simply put, we're going to solve the determinant of a minus lambda in equals 0. Right? We're going to solve the characteristic equation for lambdas, for all of our lambdas. Once we've done that, we plug them back in, and we find the null space of a minus lambda I for each value of lambda. And that's the process for finding the eigenvalues and eigenvectors. And that completes the lecture.